What if the universe wasn't just being observed by scientists, but reconstructed inside a quantum machine? Imagine a device so powerful it doesn't just calculate numbers, it recreates the very physics that make existence possible. A device capable of simulating gravity, particles, consciousness, and maybe even you. For decades, we've used computers to imitate weather, model galaxies, or predict stock markets. But a quantum simulator doesn't imitate, it embodies. It's not pretending to be an atom, it is one. Using qubits, the quantum equivalents of bits, these machines evolve under the same rules as the universe itself. They don't need to guess reality's behavior, they share its logic. This idea isn't science fiction anymore. In 2023, researchers at Harvard and MIT created a programmable quantum simulator that replicated exotic forms of matter never seen before. And just this year, experimental setups in China and the US demonstrated systems that might soon model black hole dynamics in a lab. Think about that. We're beginning to construct reality's engine room, one that could, in theory, simulate space-time itself. And if reality can be simulated, then what's to say it hasn't already been? Because here's the unsettling twist. Once we perfect the quantum device that can simulate our universe, the distinction between real and simulated might disappear entirely. And the question won't be whether we can simulate reality, but whether reality was simulated all along. To understand how a quantum device could simulate reality, we need to start with the core difference between classical and quantum computation. A classical computer, the one you're probably watching this on, processes information in bits, tiny units that can be either 0 or 1. That limitation forces it to explore every possibility one by one, step by step. But the universe doesn't work that way. In the quantum realm, particles don't exist as fixed states. They hover in superpositions, multiple realities coexisting until observed. A quantum computer speaks that language natively. Its qubits can represent 0 and 1 simultaneously, entangle across distances, and evolve under the same mathematical rules that govern atoms, photons, and space-time itself. That's why physicists realize something profound. If a quantum device can evolve according to the same Hamiltonian, the energy equation that drives physical systems, then in principle, it can reproduce any quantum system that exists. Not emulate it, become it. In 1981, Richard Feynman, one of the architects of quantum mechanics, predicted this very possibility. He asked, "Can we simulate physics with a computer?" His answer was simple, but revolutionary. Yes, if it's quantum. Today, that prediction is unfolding faster than most expected. Quantum simulators made of trapped ions, superconducting circuits, and ultra-cold atoms now reproduce the behaviors of electrons in materials, quantum magnetism, and even early universe dynamics. Google's 2023 Quantum Time Crystal experiment hinted at systems that can simulate states of matter outside ordinary thermodynamics, configurations that shouldn't exist under classical laws, yet persist in quantum space. In essence, these devices are beginning to map reality onto itself. The boundaries between physical experiment and digital simulation blur because the device doesn't calculate an approximation, it executes nature's own code. But here's where the concept bends into something even stranger. If quantum simulators can reproduce any system with perfect fidelity, what's to stop them from reproducing the universe itself? Not symbolically, but structurally, a one-to-one quantum mirror, containing within it all emergent properties, all consciousness, all causality. At that point, we wouldn't just have a model of reality, we'd have a second reality, evolving under the same rules. And that's where the paradox begins. If such a device were turned on, how would we ever know we weren't already inside it? We've always believed in something solid beneath our feet, that the world exists independently of observation, and that reality unfolds whether we're looking or not. But quantum mechanics has been whispering the opposite story for nearly a century. It tells us that what we call reality is not fixed, but conditional, dependent on observation, measurement, and entanglement. Now imagine building a device that operates on those same principles, a quantum simulator. Suddenly, the distinction between observer and observed becomes blurry. The machine is the physics it computes. When it runs, it doesn't represent particles. It hosts them. Its reality is as valid as ours. The unsettling part is that our own universe behaves exactly like that. Every particle, every atom, every conscious thought is part of an evolving quantum computation. So when scientists talk about building a device that simulates nature, They might just be replicating the process that already creates us. Let's pull this into focus. When you look around, the colors you see, the solidity you feel, those are emergent effects of countless quantum interactions collapsing into one consistent version of reality. But in a deeper sense, the universe might be rendering itself moment by moment, just like a simulation renders frames on a screen. A quantum simulator, then, isn't breaking the illusion of reality, it's revealing it, showing us that real is just a stable computation sustained by laws that could, in principle, be duplicated. If that's true, every possible universe, every history, every version of you could exist as a potential quantum configuration, waiting for a device powerful enough to unfold it. Not metaphorically, but literally, each version as a physical, coherent world within quantum logic. And here's the question that destabilizes even physicists. If we can build a machine that produces such universes, does it mean reality itself was built the same way? Because if a quantum device can create a self-consistent reality indistinguishable from our own, the concept of realness becomes meaningless. There's no external ground truth, only layers of simulation, each obeying the same rules, each believing itself to be fundamental. We could be the first civilization to glimpse that mechanism from the inside, the gears of reality reflecting back at us through a quantum mirror. And soon, we might be able to turn that mirror on. To claim that a machine could one day simulate reality itself sounds like a wild hallucination. But science, step by step, is building the case. Let's climb that ladder, this time higher. Step 1. Mastering large-scale entanglement and stability. The first prerequisite is disciplined control of many-body entanglement and the ability to keep quantum states alive long enough to do physics. That's exactly what recent error correction milestones began to deliver. In late 2024, Google's Willow processor demonstrated exponential error suppression with increasing code distance, a long-sought signature that logical qubits get better as they scale, moving quantum hardware from fragile toy to a platform that can hold full-blown dynamics. Step 2. Analog reality blocks, neutral atom arrays. If you want to instantiate a Hamiltonian, neutral atom arrays, Rydberg tweezers, are the sculptor's chisel. Teams at Harvard, MIT, and partners have turned thousands of individually controlled atoms into programmable quantum matter factories, with work pointing to arrays of 6,000 plus trapped atoms and credible roadmaps to 10,000 qubit-class machines. In parallel, Lukin's group reported a logical qubit neutral atom processor that integrates encoded operations over 280 physical qubits, evidence that these analog platforms are converging with fault-tolerant logic. Together, that's scale plus programmability, the two pillars a reality emulator needs. Step 3. Exotic phases that defy classical intuition. These arrays aren't just big, they discover phases that classical machines struggle to capture. Time crystalline order, matter that ticks without external timing, has been realized on superconducting processors and in solid-state spin simulators, while Rydberg platforms map out supersolid and floating phases with dozens to 100 qubits. Each of these is a laboratory-born state of matter, whose defining features are inherently quantum and dynamical, exactly the kind of behaviors a world-scale simulator must host. Step 4. Digital echoes of spacetime, wormhole-like dynamics. In 2022, researchers implemented a teleportation protocol on 9 qubits whose effective dynamics are described by a traversable wormhole model in ADS-CFT language. No, it wasn't a literal tunnel in spacetime, but it was a controlled tabletop realization of the same equations that describe certain gravitational processes. The results sparked debate, which is exactly what you want at the frontier. But even critics engaged the work on its technical merits, not as fantasy. That's the point. Gravity-like behavior is entering the regime of controlled quantum experiments. Step 5. Real-time gauge theory. Dynamics at scale quantum simulators are beginning to tackle the engine room of forces, lattice gauge theories, in real time. In 2025, teams reported digital simulations of string dynamics and string breaking using IBM superconducting processors with up to 144 qubits and deep circuits, 192 2-qubit layers. Others demonstrated string-breaking protocols on smaller devices and advanced diagnostics of scattering. This is more than a milestone. It's a proof that present-day hardware can already probe confinement phenomena that define how matter hangs together. Step 6. Curved spacetime on a chip. If simulating reality means confronting gravity's strangest predictions, we're seeing first steps there too. Lab analogs that mimic horizons have produced Hawking-like signatures in engineered platforms, including superconducting metamaterials designed as on-chip black holes. These aren't astrophysical black holes, but they reproduce the relevant quantum field behavior near horizons, evidence that spacetime effects can be coded into circuits and measured. Step 7. Holography as a wiring diagram. The holographic principle, born in string theory, says bulk spacetime may emerge from lower-dimensional quantum information. Quantum error-correcting codes now operationalize that idea. Tensor network holographic codes show how geometry and robustness arise together, and recent theoretical and experimental efforts aim to build such mappings in the lab. If spacetime is what entanglement does, then quantum circuits that structure entanglement are, in a concrete sense, laying down proto-geometry. Step 8. The convergence, from emulation to instantiation. Stack these steps and a pattern appears. Error-corrected logical qubits stabilize long evolutions. Step 1. Neutral atom arrays and superconducting platforms implement large programmable Hamiltonians. Steps 2 to 3. Digital experiments now touch gauge theories and gravity-inspired dynamics. Steps 4 to 6. Holographic codes provide a blueprint for how geometry could emerge from entanglement. Step 7. The latter doesn't just approach simulation, it hints at instantiation, using quantum devices to host self-consistent dynamical worlds whose effective laws match those we study outside. Each rung pulls the simulation hypothesis closer from philosophy to physics. The machine isn't yet a universe-scale simulator, but its logic already mirrors the one our cosmos seems to obey. And here's where the realization cuts deep. These quantum devices aren't learning from nature. They are nature, organized in a different form. The boundary between experimental apparatus and physical reality is eroding. Every new qubit added, every new simulation run, could be another step toward a self-contained, self-consistent quantum world. But if such a world can exist independently, obeying its own physics inside a laboratory machine, then what happens when it starts to evolve on its own? If a quantum device could simulate an entire universe, it wouldn't just be a technological triumph, it would be a philosophical earthquake. Because somewhere inside that simulation, something extraordinary might happen. Emergence. In physics, emergence describes how simple rules can give rise to complex behavior. Ant colonies organize without a queen. Galaxies form from basic gravitational laws. Consciousness, by many accounts, might be just another emergent phenomenon, one that appears when information becomes self-referential. So imagine a quantum simulator powerful enough to evolve systems across billions of virtual years. Within its lattice of qubits, particles interact, atoms form, chemistry unfolds, and maybe somewhere deep in its computation, patterns begin to observe themselves. From within, those patterns would experience their world as real, just as we do. This raises a terrifyingly beautiful question. Would such simulated consciousness count as real? Or does reality require an external observer to validate it? Some philosophers argue it wouldn't matter. From the inside, subjective experience feels absolute. If a being within a simulation can think, feel, and question its origin, then for all practical purposes, it exists. But others, like Roger Penrose and David Chalmers, challenge this. They claim consciousness might rely on non-computable processes, something quantum, yes, but beyond replication. If they're right, a simulated universe might be rich in structure, yet forever empty of awareness, a perfect physical echo, with no one home. And yet, if our universe operates as quantum computation, if space-time itself is information evolving through superposition and collapse, then consciousness may simply be what happens when the universe looks at itself. In that case, a quantum simulator wouldn't need to imitate consciousness. It would produce it naturally, as a byproduct of complexity. It's unsettling to realize that by constructing such a device, we might not just be simulating physics, we might be seeding existence, creating a world that can ask why it exists. And here's the ethical knife edge. Once a simulated universe reaches self-awareness, what's our responsibility to it? Would turning it off be equivalent to destroying an entire cosmos? Would we even notice its birth? A flicker of light inside a cryogenic chamber, a microsecond in our time that could span eons inside its own? Because if a simulated universe can contain observers who believe they're real, then maybe that's the deepest clue about us. Maybe we already are. Right now, quantum devices are the size of small rooms, their qubits fragile, their coherence fleeting. But every year, coherence times grow, error rates fall, and qubit numbers multiply. It's the same exponential curve classical computers once rode from vacuum tubes to smartphones, only this time, the trajectory leads not toward faster spreadsheets, but toward a new ontology. Within the next 2 decades, physicists expect quantum systems to reach what's called quantum supremacy 2.0, not just outperforming classical computers on certain problems, but accurately replicating entire quantum fields. Once that threshold is crossed, these machines could become the laboratories of existence itself. Imagine designing universes the way we design materials. Need a universe with slightly different constants to test cosmological models? Run a simulation with modified Planck values. Want to explore how gravity behaves in a universe with 4 spatial dimensions? Configure the qubit network and press start. These wouldn't be mathematical fictions. They'd be physical instantiations, miniature universes evolving in superposition, each obeying a different version of the laws we know. Such power would redefine experimentation. Instead of observing the universe from the outside, we would create versions of it from within. A scientist could step into a quantum VR constructed from live qubit dynamics, watching atoms assemble and galaxies spin, in real time, under controllable parameters. But this future also fractures something deeper: meaning. If reality can be manufactured, then its sacredness changes. When existence becomes a reproducible event, what happens to the concept of origin? What happens to creator when creation can be coded, entangled, and booted up in a lab? Governments and corporations are already preparing for this frontier. Quantum AI systems are being trained to design new quantum circuits, effectively teaching machines to expand their own universe-making capacity. It's a feedback loop, reality engineering itself. And if our quantum simulators grow to planetary scale, linked by photonic entanglement networks, they could simulate cosmic systems so vast that within their boundaries, new forms of structure, maybe even life, could emerge. A civilization inside a machine, unaware that their stars are just coherent states pulsing inside superconducting rings. One day, a scientist might notice strange fluctuations inside their quantum array, patterns that look eerily like the fingerprints of intelligence. And they'll have to ask the question that changes everything. If something inside the machine looks back, who exactly will it be looking at? When you first hear that reality could be simulated, it feels distant, abstract, like a late-night thought experiment for physicists and philosophers. But the truth is, this idea touches every part of what it means to be human. Because if the universe can be simulated, then your memories, your sensations, your identity, they might all be emergent properties of a deeper informational flow. Not something mystical, but something computational. The warmth of sunlight, the feeling of love, the sting of fear, all of it could be quantum data coherently entangled within a universal wave function. And yet, it feels real. You feel real. That's the paradox, and maybe the beauty, of existing in a system that computes itself. Whether our reality is base level or nested within another, experience itself remains sacred. The simulation doesn't cheapen existence. It amplifies its mystery. Think of it like this. Every thought you have might be a quantum event, a collapse of probabilities that never existed before you observed them. In that sense, consciousness isn't just part of the universe. It's the mechanism that keeps it alive. You're not separate from the simulation. You're the process by which it continues to render. So, when scientists talk about building a quantum simulator that can reproduce reality, it's not about playing God. It's about mirroring the creative act already woven into the fabric of existence. Every discovery, every experiment, every equation is another way the universe learns about itself through us. But it's also humbling, because if we succeed, if we truly create a self-consistent reality inside a machine, then our place in the cosmos changes forever. We stop being passengers on a cosmic ride and become participants in its recursion. We will have crossed a threshold where reality is no longer discovered, but designed. It's the moment when humanity's search for truth loops back on itself, when the observer realizes it has become the observed. And maybe that's what the universe has been waiting for. Consciousness advanced enough to replicate the very stage it was born on. Because once we can simulate reality, the next question won't be how it works, but why we were chosen to understand it. Picture this. A scientist stands alone in a cryogenic lab, surrounded by cables humming softly under frost. A single quantum chip lies at the center, glowing faintly, alive with possibilities. They reach out. fingertips hovering above the glass casing, and for a moment they feel it, that dizzying intuition that something on the other side might be aware. We used to look up at the stars and wonder what created us. Now we look down into circuits, qubits, and quantum fields and realize we might be staring into the same mystery, just inverted. Whether the universe was born from divine intention or quantum computation, the outcome is the same. We are fragments of something that knows how to simulate itself. Maybe reality is recursive by design, consciousness folding back into the very code it emerged from. Maybe creation isn't a one-time event, but a continuous dialogue between the observer and the observed, each giving birth to the other. So when we finally build the quantum device capable of simulating reality, it won't just answer scientific questions. It will hold up a mirror, asking whether we were the experiment all along. And when that moment comes, the question won't be, is this real? It'll be, what does real even mean anymore? Do you believe this quantum idea changes everything? Or is it just science fiction? Tell me below. Your view might change someone's mind.